so I wrote a matrix down, a 4 by 4, and I just said find the determinant. So from last class, we did Laplace expansion, and you would pick the row or column with the most zeros to do that. Okay, so we could do, we're not going to, but we could do expansion on maybe row 3 because it has 2 zeros, or you could do column 2, right? Or column 3, yeah. On, let's just write that, either row 3, column 2, or column 3, since they all have 2 zeros. Now, that being said, one of the row operations we talked about in the last part was that if we switch 2 rows, that it changes the sign, and you would just have to remember that if you did that. Is there an opportunity to switch 2 rows and then get a row or column with more than 2 zeros? Can we do that somewhere? So we can't switch 2 rows and do it, but could we switch 2 columns, or still won't work? No. So the row switching won't work. The other row operation that we mentioned so far, we actually talked about all 3 row operations, but the other one, if you add or subtract 2 rows, or even a multiple of 2 rows, it doesn't actually change the determinant. The determinant stays the same. So could we add 2 rows or subtract 2 rows and make another 0 somewhere? The more zeros we have, especially in a big matrix, the better. So we could add which rows? Adding rows does not change the determinant. So if we add row, so if we make a new, say, row 1, and we say that is row 1 plus row 2, that will make a 0 in that first spot. Right? So, and you have to pick one of the rows for it to replace. It doesn't really matter which one, but you have to pick one. It doesn't, when you add the 2, it has to replace one of the 2 rows. The other one stays the same. So if we add these, that would be a 0, 2 plus 0, 1 plus 0, 5, and then the rest all the same. Okay. Now what do you think? Is there a better option now? We have a lot of zeros. We could just pick a row and do Laplace on it at this point. You could switch some rows. You could try to make it upper or lower triangular. You could try to make another 0. You can multiply a row by a constant, but that does change the determinant by that constant. So then you have to divide. That one I find people make mistakes on. So we could, for example, multiply this by 2 to get rid of the fraction if we wanted to. Then our new matrix would have a determinant 2 bigger. So then we won't, when we want the original, we'd have to divide by 2 to get back to the original. Which people get confused. Am I supposed to divide or am I supposed to multiply? And they usually do the opposite for some reason. So I don't like that row operation exactly. But let's say we did this along, let's do Laplace to remind you anyway, along row 3. Okay, so we'll write that out. I'm going to circle row 3. So we need to know the position it's in, whether it's plus or minus. And the signs alternate. Would that 5 be plus or minus? This is in row 3, column 1. What's 3 plus 1? 4. So this would be negative 1 to the 4 times 5 times the minor. So what's our minor? Cross off that and this, and the 9 numbers that are left are the minor. And then what's the next element in row 2? A 0? We can ignore it, because that won't change anything. Another 0, and then we have a 1. So what position is that in? That's in row 3, column 4. So 3 plus 4, 7. So that'll be a negative, times 1, the number there is 1, times the minor. So we would cross that row and that row off, and we have 0, 2, 1, minus 1, 0, 1, minus 2, minus 1, 1. So this is 5 times this determinant, minus 1 times this determinant. That would give us our answer. So let's just get our answer from here by doing our diagonals. So the first one, 2 times 1 times a half. And the next, 1 times 2 times negative 1. And the third, 0, 1, and 0. And then from that we would subtract backwards. All right, so backwards we have 5 times 1 times minus 1. Here, 0, because there's a 0, you don't need to write it out. And then 2, 2, and 1. All right, so what do we have? 5 times 1 minus 2 is negative 1, minus 5 plus 4 is minus 1 again, 0. So 5 times 0. Good enough. This one. 0, 2, 1, and negative 2. And then 1, negative 1, negative 1, and 1, 1. And then subtract, going backwards, 0, 2, negative 1, and 1, and 0. So here we have minus 4 plus 2, minus 2 times minus 1. This one's 0, 2. Oh, minus 4 plus 2.
Minus 4 plus 1, plus 2.
Oh, yeah, minus 3 plus 2 minus 1 is 1. There, is that right now? 1. That's very messy. So determinant is 1. Right? So I'm messy down at the bottom there. Okay, so let's actually write out the row operations and how it changes the determinant. So interchanges 2 rows, changes the sign. 2. Multiply or divide a row by a non-zero constant changes the determinant by the same constant. So, for example, if you had A, and you didn't multiply A by 2, but one of the rows in A by 2, okay? So, like, say you did the row operation, row 2 is 3 row 2. So you multiply the second row by 3. How does that change the determinant? So the determinant of A is some number. The determinant of the new A, right, after your row operation would be what? 3 times the number. So then you have your new determinant. What would you do to get the original that you were looking for in the beginning? Divide it by 3, right? So you've changed it, and then the one you found is 3 bigger. So to get back to the one you wanted originally, you would have to divide by 3, all right? So people get confused because they say, oh, when you multiply something by 2, you have to divide it by 2. But that's because your new matrix is 2 bigger, so to get back to the original, you have to go back by 2, right? So it's not actually confusing, but people, if you're not thinking about what it's actually doing to the new matrix, you're getting one that's 2 bigger. That was only multiplying one row, right? If you multiplied the whole matrix, then it's 3 times whatever size it is. And 3, replace a row by that row added to a multiple of another row does not change the determinant. So when I use row operations to do a determinant, I try to stick with this one and make a bunch of zeros because it doesn't actually change anything. I don't make a 1 first and then make the 0 like we do normally, or if you make the 1 first, go back and put it how it was before you made the 1 after. Right, so I don't make the 1 first to make the zeros, I just use whatever number's there. So I'm just going to show you how to do that. As soon as you make the 1, then you have to, so you've divided by that, then you'd have to multiply by that after. Okay, so example, use row operations to find the determinant. So what you're trying to do is reduce it so that you have an upper or lower triangular matrix. So put zeros below the main diagonal, and then all you need to do is multiply the diagonal. Right? That would be ideal, no matter what size. If you had a 6 by 6, if you make all of those numbers below the main diagonal 0, then you just need to multiply the diagonal. You don't need to do Laplace with all the smaller matrices to do it. Okay, so what we're going to do is row reduce this. I did put a 1 in that top spot to make it easier. So here's a 1. If we want to make that a 0, row 3 is row 1 plus row 3. That doesn't change the determinant. So you can use your new matrix. So 1, 2, minus 1, 0, 3, 1. And we add these. There. No need to go further. Start with an easy one. The determinant here is 9. 1 times 3 times 3. And since this was no change, we can use that as our determinant. Okay? All right, so we're going to write a new one, and I'm going to show you how to do the row operations. So, example 2. And if you use the other row operations, it's okay, but you have to keep track of what you did so that you can change your answer by the same thing. So remember, we're not trying to solve a system, we're just trying to make zeros, really, or make it look better. When you're trying to solve a system, you want to make a 1 and then zeros, you want to make a 1 and then zeros. This time it doesn't really matter. You don't want to go in circles, make a 0, and then all of a sudden it's not a 0 anymore, but you can do that. So, is there a logical first step that we might want to do here? Okay, so we could multiply the bottom row by 2 to get rid of the 1/2.
Add row 1 and row 3.
We could add row 1 and row 2.
And add row 1 and row 3. To get rid of the other one.
Add row, our new row 1? Or this row 1? Oh.
Add row 1 and row 2 to cancel.
Oh, yeah, and if we add row 1 and row 3, so the problem would be that that would then make that 0 a 2. Do you see it? Yeah, so stick with your first row. It's just like in row operations, look only at this first one until you're happy with it. Then move to the second one. Because as soon as you, if there's a 0 here and then you take this one and move it down, somehow it won't be nice anymore. So I would probably say, let row 1 equal row 1 plus row 2. Would that be okay? That would make 1 0. And to keep track of what we've done, I'm just going to write no change. So it doesn't matter the answer, that doesn't change it. Okay? And yes, we could multiply this by 2. So let's say we do 2 row 4. So what's the change here? 2. So if we multiply 1 row by 2, the answer is twice as big. So we need to divide it by 2. So divide by 2 is the change. Right? So in the end, we have our answer. We say, okay, we don't need to change it for this one. We need to divide it by 2 for this one. We need to change the sign for this one. And you go down all your changes and do all your changes to it. So let's do these 2 row operations. So if we add these together, I'm going to write it in row 1. So that would be 0, 5, -3, and 1. And here I'm going to multiply by 2. Okay, so I actually ended up losing a 0 there. Right? We maybe would have rethought that, made it row 2 instead, but I already did it, so let's just leave it. And that would have gotten rid of that 0 either way. So, okay. So, what about making this one into a 0? Using this 1. Yeah, so we'll use this 1 to make that into a 0. So we're going to change row 2 by taking 2 row 4 and add that to row 2. So 2 row 4, 2, 0, -4, and -8, plus row 2. Okay. You could switch the rows around if you didn't like what you had done, but you can still do that. We're done with this column. We don't want that to change again, right? Because we've done with that one. Can we make some zeros over here? What would be a good number to use to make the zeros? Maybe that -1. That'll be easy to use. So if we use this -1, but don't change it to a 1. You can if you want, but then you have to change the sign later. If we use this, how do we make that in row 2, that 4? That's a 4. This needs to be a -4. So what do we multiply row 3 by? Just 4, because it's already a negative, and we need it to be a -4. So just 4 times row 3 plus row 2. And what about this one? That's in row 1, so that's a 5. This needs to be a -5, so a 5 times row 3 plus row 1. And if we do those, we're going to have zeros here. And these are all no change. No change.
Can you do R3 plus, or like R2 equals R3 plus R1?
No.
No.
That's getting a little weird. I have to think about that. So don't add 3 rows. Yeah.
So that would make
You could do 1 and then do the next, but I wouldn't add 3, no. Okay, 5 row 3. 0, -5. 5 times 2 is 10, and 5 times 3 is 15. Plus row 1. You can try that yourself and see if you get the same answer. I think it would be okay, but I don't want to say that out loud in case it's not. I'd have to think about it more. Okay, and 4 row 3 plus row 2, 0, 0, minus 12 and minus 19. What would be the only number we need to get rid of if we wanted this to be a lower triangular matrix? That's 7. Do you see it? So here's our diagonal. Yeah, so I've almost, and you could be doing it the other way. I did it on purpose upside down to make it a little harder. So, yeah, so do you see that if I made this 7 into a 0, now, which row do you have to do? So you have to use to do that so that these zeros don't change. This is where it's important. You're going to add this row to other rows. If you add it to this, what's going to happen here? You're going to end up with a 1 there. If you add it to this one, you're going to get that number up there. Never. When you do it with this row, they both have zeros. Do you see that that would be okay? So you're going to use this -12 to make a 7. So you could divide by -12 and then multiply your answer by -12. Oh, what's it supposed to be? A 4? Oh, do I have the signs wrong here? This was 4, so these should have been positive. And this should be a 4, and this should be a 5. Thank you for correcting that before I did it. So this should be a 4, and this should be a 5. So hopefully you have a pencil, you can just erase that. Good? All right, so you can divide by 4, make it a 1, then use the 1 to get rid of 7. I'm not going to do that, I'm just going to show you how to not do that. So here, I don't have room, so I'm going to say we're changing row 3. Normally, what would you do to that to make it a 1? To the 4. Divide by 4. So we need to divide, oh sorry, we're not changing row 3, we're changing row 1. So, row 1. So we're changing row 1. This is row 2. So normally we would have made a 1 here by dividing row 2 by 4. So divide row 2 by 4. And then if we did that, we need to then multiply row 2 by -7. So you divide it by 4, that makes a 1, and then multiply it by -7. So -7 over 4 row 2 plus row 1. Yes. So we said you could use this, but then what happens is when you add this row to that, you end up without a 0 here anymore. Right? You need to look for the one that won't change the zeros. So once you move out of this row, you don't ever want to use this row again. Once you have left that zeros everywhere else, you only want to use these 3. Once you move here, you don't want to use these, neither of these, because they'll now make these things into zeros. And then when you're in here, you need the one with zeros. So -7 over 4 row 2. 0, 0, -7 over 4, -7, -7 over 4 times 5 is -35 over 4. Plus row 1, 16, and 16 over 16 times 4, 64. 15 times 4 is 60, 4 more, yeah. 64 minus 35. I always get it backwards. 29. Okay. Yeah. Okay. 29. So if we write that in, 0, 0, 0, 29 over 4. 0, 0, 4, 5. 0, -1, 2, 3, and 1, 0, minus 2, minus 4. Now, because I did one change way up here, divide by 2, once I find this determinant down here, I need to divide it by 2. So, the determinant, this is a lower triangular. So the determinant is 1 times minus 1 times 4 times 29 over 4, which is -29. So the determinant of the original A is minus 29 divided by 2. That was the only row operation that we did that needed a change. We didn't swap rows anywhere. We just made zeros after that. Okay. So if you have a great big matrix that you need to find the determinant of, you would never jump right to Laplace because, like I said, if you had a 6 by 6, the smaller matrices in that, the minors, are 5 by 5s. And for each 5 by 5, you would need to do Laplace, and in that would be all 4 by 4s. And then you would have to do Laplace on those and get all 3 by 3s. And then you could do the 3 by 3s. But you might have 20 lines to get there. So making zeros or using row operations will reduce it. The more zeros you get, you don't need to reduce it all the way. Like, you say, well, this is only a 4 by 4. At this point right here, you could do Laplace on column 1, and your minor is a 3 by 3, and you know how to do a 3 by 3 using the diagonals. So you could just go to that. Although this has no zeros in it, so it would be a lot of numbers. A little further, and you say, okay, I'm giving up here, I'm going to do it on this, but my minor, if I was using Laplace and that was my only number in that row, my minor has a row of almost of zeros. So the minor would actually be quite easy to find the, right? So the more zeros, the easier it is. If you reduce it all the way to upper or lower triangular, you do not need to do a diagonal. So don't make the zeros above and below your ones, just on one side. Either above or below, but not both. We had this, I think this is the same one I wrote before. Let me just double check that I wrote it the same, because we found the determinant of this already. Yeah, so we found the determinant of this was 1. Okay, so here's our matrix, and we know the determinant of it is 1. Okay, so I'm going to say find the determinant . All right, so we need to be able to see all of these. Or maybe you would just write down A so you can look at it. I think you can still see them all that size. Okay. So what I'm saying is, here's A. We already figured out the determinant for A. And I'm telling you that B, C, and D are something done to A so that you can figure it out without doing any calculations. So look at B. Can you see what I did to B from A? Which rows? Row. And the rest is the same? Yeah. So what does this do to a determinant? Changes the sign. So determinant of B is -1. Changes the sign. So switching rows changes the sign. So instead of 1, it's -1. The next one. So the rest the same? So multiply row, so the row operation was row 4 is 2 times row 4? So how does that change the determinant? Be careful. We're not trying to find the determinant of this one, knowing that one. This one, is it bigger than that by 2 or smaller than that by 2? Bigger. We multiplied by 2. This is now bigger by 2. What you're thinking, and that's why I said, everyone gets this one confused. If you've changed it to find this one, right, you're looking for the determinant of A and you're using 1, then you have to divide to get back to the original. But we're not, we're just trying to find the new one. So this one would be 2 times the determinant of A. Just 1, 2, because we multiplied 1 row by 2. If I'd multiplied 2 rows by 2, 2 squared. 3 rows, 2 cubed, and 4, all 4 would be. So this is 2 times 1. And what about D? Right. 2 to the power 4 times the determinant of A, because D is 2 times A. The whole matrix multiplied by 2. So this would be 16 times 1. Right. Now some of the ones they give in the book are a bit hard to see what they changed. I find when they switch columns, I can't see it right away what they did. So for example, if I gave an E, so you maybe can't see A and E at the same time there, but so here's A and here's E. You see I switch column. I just told you I was switching columns, so you should be able to see that I switched column 2 and column 3. That switches the sign. So all of these can be done to columns instead of rows because the transpose is the same. So it's sort of a row operation, but after you've transposed it. So these columns switch, so they would switch signs. So the determinant of E is negative determinant of A. Okay? So there's some in the book like that. It gives you a matrix and then it asks you to not do the calculations but to actually use what you know about determinants to find the determinant. They obviously wouldn't give you the inverse because you can't just look at it and know that that's the inverse, but it would just be some row operations done to it. So that's it for 3.2.